So here we are in Chapter 6. Chapter 6 will introduce us to a couple of new methods of tracking where our electrons are. And the two methods are called valence bond theory and the molecular orbital theory. And in this video, this particular one right now, we're going to look at the valence bond theory. So let's get started. Now, we've worked with the Lewis dot method enough to know that it helps us identify the number of valence electrons, make predictions about how atoms come together, as well as predict the shape of a molecule that is created as a result. And we've done this for methane several times, and this is what we end up with. Lewis dot method even allows for us to predict the number of bonds that will likely form, such as this double bond right there. And this method is pretty accurate, but what it lacks is specificity. It doesn't tell us much about how these bonds form or how they exist in space. And that's why we have valence bond theory. So let's start by asking the age-old question, why does a bond form? Well, the answer pretty much is that it forms because it lowers potential energy of a system. But how does that happen? Well, let's think about the forces that are involved. So let's take carbon, for example. In the nucleus, we have positive charges coming from the protons. And orbiting the nucleus, we have electrons with their negative charges. And these electrons are held in a fairly close orbit. Well, what will it take for hydrogen to create a union with carbon? Because keep in mind that hydrogen is going to show up with its positively charged nucleus and its negatively charged electrons. And the like charges will have a repulsive effect, and the opposite charges will have an attractive effect. Well, whatever happens, we know that the potential energy of the system has to be lowered as a result of that union. And we're going to look at that a little bit more. But for now, we know that's one of the things that needs to happen. Another thing that needs to happen is that there needs to be a balance between those attractive and repulsive forces. And indeed, measurements have shown there is this sweet spot that exists between two atoms where this is the case. And the last thing that needs to happen is that there has to be an overlapping of the orbitals so that the electrons get shared and a bond gets created. And in fact, all of these things must happen to ensure that a bond is formed. A covalent bond is formed. So let's begin this part of the journey by revisiting the good old orbital diagram. So for hydrogen, it's a pretty simple orbital diagram. We know that the one electron of hydrogen lives in the 1s orbital. Sulfur has 6 valence electrons, and they're going to occupy the 3s orbital as well as some of the 3p orbital. Remember kids on the bus and all, Pauli exclusion principle? And as far as hydrogen bonding with sulfur, we could say that maybe this hydrogen comes over here and takes this seat on the bus, and that this hydrogen comes over here and takes that seat on the bus. And that would give us a molecule that looks a bit like this, kind of a bent molecule with those two non-bonded electron pairs hanging out up at the top. So that seems pretty straightforward. Yeah, okay. Now let's do the same thing with our friend methane. So here's the diagram for carbon, and here are the orbital diagrams for the hydrogens. And we can say that this hydrogen will come over here and grab this seat on the bus, and that this hydrogen can come over here and grab this seat. But what about these other two? Are they going to couple up together and come and take this seat on the bus? I mean, aren't they supposed to bind with carbon's electrons? Well, we know that the shape of this molecule is tetrahedral. We have seen this to be true. Lewis dot theory bears it out. So what's happening? To answer that, let's bring up an energy chart and drop in the orbitals for carbon. So with carbon's energy diagram, we have these p orbitals having a higher energy than that s orbital. Now, in order for carbon to bond with another atom, one of the things that must happen is for there to be a lowering of the potential energy of the system being the union between two atoms, carbon and something else. Now, in order for this to happen, nature does something interesting. Nature allows carbon, as well as any other atom, to rearrange its valence electrons in an act called hybridization, the result of which is the lowering of the energy state for that element. This means that carbon is able to take its valence electrons and spread them out, which lowers energy. And it makes those valence electrons available for bonding. So where did these four hybrid orbitals come from? Well, one orbital was previously known as the s orbital, and the other three were previously known as the p orbitals. And because we have one of these hybridized orbitals coming from an s and the other three coming from p, this is known as an sp3 hybrid. So how is it that carbon does this? Well, when carbon's energy diagram looks like this, carbon looks like this. And in order for the energy diagram to move to this, carbon's orbitals have to change shape. The tight orbital of the electrons changes from that to something that looks a little like this, a little bit looser orbital that moves a little further away from the nucleus. And these slightly larger orbitals allow for the electrons to move into slightly larger orbits. And these slightly larger orbits allow more real estate for finding that sweet spot between attractive and repulsive forces, and it ensures an overlap of orbitals with another element. Thank you very much, valence bond theory. Well, let's do the same thing with our friend, the ammonia molecule, NH3. Well, if we do the Lewis dot, we can see that it looks like this, and we've worked with this molecule enough that we know that it's going to bond with those three hydrogens and that it's going to have that lone pair on the nitrogen, and it'll render a molecule that has a shape that's known as a trigonal pyramidal. It's not a true shape because the influence, it's not what I call a true shape, because the influence of those lone pair of electrons is going to basically bend the shape. Well, if we do the same thing and look at what valence bond theory allows, we can bring up an energy chart and drop in the energy diagram for nitrogen's valence electrons. So what's going to happen when those electrons rearrange and go into their hybridized state? Well, with carbon, we had something that ended up looking like this, where each electron had its own orbital. But we don't have 5 different unions occurring on our nitrogen like we had 4 on carbon. No, we've only got 3 bonding electrons that are available for nitrogen, and 2 of them are going to have to stay in an orbital by themselves. So instead of having all 5 of nitrogen's electrons spreading out into a hybridized orbital, nitrogen is going to end up looking a bit more like this, where the 2 non-bonding electrons are going to stay in a high energy orbital, a high energy p orbital, and we're going to have a hybridization occurring with 1 s orbital and only 2 of the remaining p orbitals. As a result, this ends up being called an sp2 hybrid because it involves the s orbital and only 2 of the p orbitals. And what about our friend phosphorus pentachloride? Well, already you're probably having some alarm bells go off because we have phosphorus being bound to 5 different other elements. If we bring up the Lewis dot for phosphorus, we can see that in fact it does have 5 electrons in its valence. And the thing that is that allows phosphorus to do this is that it exists in the third row, which means it has a d orbital. So phosphorus can in fact bind with 5 chlorines, and it ends up with in a molecule looking very much like this. So let's bring up the energy chart and drop in the diagram for phosphorus. Well, we know that with those 5 electrons, that this gonna 2 of the electrons are going to occupy the 3s orbital, and the other 3 are going to occupy the 3p orbital, and that's the total 1, 2, 3, 4, 5 electrons. But because this is in the third row, we know that there is an existence of a 3d orbital, which means we can harvest some of those potential unoccupied orbitals and allow the 5 electrons that live in the valence of phosphorus to spread out. So when phosphorus does a hybridization, one of the things that it can do is create something like this, where one of those hybridized orbitals is coming from the s orbital. 3 of the hybridized orbitals are coming from the p, and we've captured one of the d orbitals. And what we've created is something known as an sp3d hybrid, which means an orbital comes from one s, 3 orbitals come from a p, and we've harvested one of the d's. Well, what about sulfur hexafluoride? Well, if we bring it up, here's the Lewis dot for sulfur. Sulfur is in the third row, which means that it's going to have that mysterious unoccupied d orbital, right? And it can, in fact, bind with 6 other elements as a result of that. Going to look something like that. So if we bring up sulfur, we can see how it's going to occupy its orbitals. Even though it's occupying only s and p, it does have that d orbital hanging out there, not occupied, but it's out there and you can move into it. And in fact, it does. When sulfur hybridizes, it creates 6 hybridized orbitals, or it can, and in this case it does. One of those orbitals is coming from s, 3 of them are coming from p, and in this case we've recruited 2 from the d suborbital. And as a result, the hybrid that we've created here is an sp3d2 hybrid. So a moment ago I said that we could take a standard orbital, and once it underwent hybridization, it changes shape and it actually expands a little bit and becomes a little bit larger, allows the electrons to move a little further away from the nucleus, and as a result it allows for finding that sweet spot and allowing for a greater area of an overlap with another atom. Well, if we apply this to nitrogen, we can bring up nitrogen and then we can plug in its 3 oversized hybridized sp2 orbitals and then drop in 3 hydrogens so that they overlap. So this is basically what this theory is telling us is happening here. But these things happen in 3 dimensions. So there's an orientation that happens with particular types of bonds. So in this part of the lecture, we're going to actually look at what's happening right here when the nitrogen and the hydrogen come together. The type of bond that exists between nitrogen and each one of the hydrogens is called a sigma bond. And the definition of a sigma bond is when the interacting atomic orbitals point along the axis connecting the 2 bonding nuclei. A simpler way of saying that is you have a sigma bond when you have a straight shot between the 2 nuclei of the atoms that are being connected. It's just a straight shot between them. And this is important because even though these are microscopic structures, they still have orientation. They still have 3 dimensions. And how things come together is important for them, and ultimately is important for us in understanding how they work. So a sigma bond then is a bond that is happening along a particular axis, and we can actually think of it as 2 atoms coming together in something like a fist bump. They're meeting head on, fist bump, straight head on together. And we can get real specific when we talk about what's happening with nitrogen and hydrogen. We could say that it is the s orbital of hydrogen interacting with the sp2 hybrid orbital of nitrogen. So we could say that we have an s subshell to hybrid fist bump happening here. Yeah, we could say that. What about our friend, the hydrogen molecule? Well, hydrogen only has an s subshell. So the type of fist bump that happens between these two guys is an S to S fist bump. You kind of get in the swing of this? You see where I'm going? Let's take a look at another one. What if we have hydrogen and fluorine coming together? Well, the active electrons for fluorine are in its p subshell. The active electron for hydrogen is in its s subshell. What do you think we're going to call this fist bump? We're going to call it an S to P fist bump. What if we put two fluorines together? Well, one fluorine is involving its p shell, the other one is involving its p shell, and you got it. They're going head to head in a P to P fist bump. So now that we've taken a run around the old sigma bond concept, let's bring up our molecules that we looked at. And what do you notice about these? Well, they don't all have the same shape, do they? And they don't all have the same number of atoms. What do you notice? Well, hopefully one of the things that you noticed, and maybe the most important thing that you noticed, is that they're all made up of single bonds. Now, are single bonds the only ones that exist in nature? Well, no, they are not. You have double bonds, right? You also have triple bonds. So if we're calling a single bond a sigma bond, what are you going to call a double bond? Well, before we call it anything, why don't we ask the question of where do they occur? Where are double bonds going to happen? Or better yet, where can double bonds happen? Well, let's bring up the old s orbital, for example. There's an s orbital. It's spherical in its shape. And we have our friend, the hydrogen atom here, with its two s subshells. Can it form a double bond? No, because the only number of atoms that an s subshell can hold is 2. And if you have a hydrogen bringing one electron to the table, hoping to find another electron to share with, it's not going to be able to create another bond within that subshell. So then that means the S subshell is a place where we cannot have multiple bonds. We can only have single bonds in the S subshell. So let's move to the next subshell, which is the P subshell. Oh, what do we see here? Well, the P subshell exists in 3 dimensions. We have that X orbital, which goes side to side. We have the Y orbital, which goes up and down. And then we have the Z orbital that comes in and out of the page. And we have electrons that can live in all 3 of those orientations. And it's in the P orbital where we can have double and triple bonds. So let's take a look at that. So what if we brought a couple of half-filled p orbitals together? Well, as long as they were in the same orientation, and these are both the px orbitals, so they're in the p subshell and they're both oriented x, when they underwent a reaction, they could create that sigma bond. That is that overlapping end-to-end form of bond. But we have 2 other orbitals in the p subshell. We have also a y and a z. Now they're not aligned in such a way that they can create a fist bump. In fact, they might end up looking something like this, where they're side by side. These guys cannot do a fist bump. They have to kind of change and do something else that looks like this. And this is what we would call a side by side arrangement. And this is what's called the pi bond. So when we look at these 2 orbitals, when we have this sigma bond, That's our virtual fist bump, and the two nuclei are in line with each other, creating that axis between the two nuclei. When we look at a pi bond, that's not the case. This is what I like to call the reach over bond, so that you have one set of electrons reaching over to another set of electrons, and it is those two side-by-sides that create a single bond. Now I know I have two lines here, but on the reach over, the top and the bottom are the same orbit. They're both occurring in the same orbit. So if we are in like the P of Y orbit, because we have a P of Y on top and a P of Y on the bottom, and the electrons can live in either the top or the bottom Y orientation, it is a single orbit. It is not two. People get tripped up on that. Don't let that be you. And with our newfound information, let's see if we can identify the types of bonds that this molecule has. Now, if we start with the carbon to hydrogen bonds, that is the black to the gray bonds, what do you think we have there? Well, if you notice, they're single bonds. And what did we say every single bond was? Well, every single bond is a sigma bond. So those are sigma bonds. That's easy enough. But what about carbon to oxygen? What about that black to red? Well, there's two bonds there. And one of them is, in fact, going to be a head-to-head sigma bond. And we could even say that maybe it's in the P of Y orbital, because it's going up and down, P of Y going up and down. So in this case, because the two P of Y orbitals are meeting head on, this is the sigma bond. Now that means that that's going to leave either a P of X or a P of Z orbital to form the pi orbital. And I just chose P of Z. It doesn't matter. I chose P of Z. So that's what's going to be what creates our pi orbital. So if we were to write all this out, we could say that we have two carbon-hydrogen bonds, both of those are sigmas, that one of the carbon-oxygen bonds is a sigma, and the other carbon-oxygen bond is a pi bond. And this is a diagram from your book regarding this molecule, and you can see that it specifies that you're going to have two sigma bonds for the carbon-hydrogen bonds, and they're showing you a really nice picture there. And then if you look towards the bottom, they're saying that your double bond between carbon and oxygen is made up of one pi bond and one sigma bond. So what about our friend the nitrogen molecule? What do we have going on here? Well, I see three bonds. And what do we know might be happening here? Well, one of the things that we know is happening here is that we have a head-to-head bond taking place that we would call a sigma bond. And because it's in the up and down orientation, I'm just going to call it the Y orientation within the P subshell. And what do you think one of the other bonds is going to be? Well, it's going to have to be a pi bond. And which of the P subshells is it going to be in? I don't know, pick one. Let's pick P of X. It'll be that one. We've accounted for two of our three bonds. What about that third bond? What do you think is going to happen there? Yep, another pi bond. And which orbital do you think it's going to be in? Well, it's going to be in the last available one, which is the P of Z. Now, do the orbitals really matter? No, they don't. I list them so that you have something to hang your hat on. You have some sort of definitive. But depending on how this thing is oriented, you could call it in any of the three orientations, the X the plane, the Y plane, the Z plane, it doesn't really matter. But one of them is always going to be in the sigma. It's going to be a sigma where you have a head-to-head orientation between the two orbitals of the two atoms. And then in the case of the triple bond, the other two are going to be pi bonds. Now, we haven't spoken much about double and triple bonds, and we're just going to take another little pass at it here. So let me ask you this. Do you think that double and triple bonds have an influence on the way a molecule behaves? Of course it does. That's why I'm asking the question. So when you have a single bond allows rotation to occur around that axis. So we see in my little animation here that one end is able to spin around freely. In fact, both ends can spin around freely and independent of each other. And that has an influence on how the molecule is going to behave and what kind of orientation it can take in space. Now, if we add to that a double bond or a triple bond, what do you think might happen? But when you have a double and a triple bond, they do not allow for that rotation because you no longer have a single axis. Now you kind of have like a secondary axis taking place. It's not really an axis. It's kind of like it's the reach over. It's really what it is. And once you've done that, you basically have tethered those two atoms in a static orientation so that there is restriction and there's no rotation that can occur. And if we look at the molecule that we have here, we have a carbon, two carbons bound together, and each carbon has a hydrogen bound to it and a chlorine bound to it. What do you think might happen with that? Well, let's just take a look. So when we look at this particular molecule, two carbons, two hydrogens, two chlorines, the thing that you might notice is that both of these chlorines are on the downward side. And what the artist is trying to demonstrate here is that both of the chlorines are on the same side of the double bond. They're both in the downward position. Now the chlorines are significantly larger than the hydrogens, and they're considered the bigger constituent is the word I'm going to use. And when the bigger constituents are on the same side of the double bond, we would call that the cis orientation. Cis, C-I-S. If we have this orientation, what is the other possibility? Well, the other possibility is when you have the larger constituents on opposite sides of the double bond. And when that's the case, they have gone across the double bonds, and we would call that the trans orientation, T-R-A-N-S, trans. Now we have the same number of hydrogen molecules, we have the same number of carbons, we have the same number of chlorines. In fact, we have the same number of single bonds, and we have the same number of double bonds. You might be inclined to think that these molecules would behave the same, but do you think they do? Of course not. If these were pieces of furniture and you were trying to put them in your house, do you think that the cis would take up the same amount of space as the trans? Absolutely not. They're shaped very differently, and as a result, they're going to have different characteristics. For example, boiling point. If we look at the boiling point of these two molecules, the cis configuration comes in significantly higher at 60 degrees Celsius, whereas the trans boiling point comes in at 47 degrees Celsius. It's quite a bit different. So yeah, double and triple bonds are going to play a role in how a molecule behaves and the characteristics that that molecule has. So what kind of question might you be asked about double and triple bonds? Well, basically it's understanding the cis and the trans orientation, and understanding that it does make a difference in the behavior of the molecule, such as boiling points. It can drive up or drive down boiling points and freezing points. So the sort of question you might see about double and triple bonds on this exam would have to do with conceptual questions. What do you understand about them? All right, and that brings us to the end of the first part of the lecture over Chapter 6. Be sure to keep an eye out for Part 2, where we go into molecular orbital theory. Thanks for watching.